Okay, in this video we're going to start graphing parabolas and exploring simple things we can do to these graphs. So the simplest parabola has equation y equals x squared, and to get a feel for what it looks like we should plot a few points. So we have of course 0 square being 0, which means it passes through the origin, so right in the middle at that yellow dot there. Then if we go to x equals 1, we have 1 square being 1, so that means there's another point there up by 1. Then for x equals 2, squaring 2 gives you 4, so that sends us 4 units up to there. And then for x equals 3, squaring 3 gives you 9, so that puts us all the way up to there. And so you can see it's getting increasingly steep. But another interesting thing about squaring is that squaring a negative number gives you a positive answer as well. So that gives us a symmetry, where the negative numbers will square to the same positive values on the left side as well. And so putting all that together, we get a curve that looks something like this. And that is our most simple parabola. Okay, so what can we do to this guy? Well, say we now put a plus 3 at the end there. What impact would that have? Well, the equation happens to start with y equals, and that's super important, because it tells us the meaning of adding 3. We are increasing all the y values by 3, because that's what we have control of in our equation. And so that means every point on our parabola needs to get boosted up by 3, and that will move the entire parabola up by 3, sending it all the way up to there. What if we change it to minus 4? Well, for the same reason, we'd be moving the original parabola down by 4, so it would look like this instead. And when our parabola starts moving, it's often easiest to keep track of where the tip of it is. We call this point the vertex. So if we were drawing this for real by hand, we'd think of the vertex having moved down by 4, then we'd just draw the sort of smiley face coming from that point. Okay, so what else can we do? We can say put a 2 in front, so multiply everything by 2. That means if we take all these y values here, remember we're controlling the y values, they would all have to shoot up to double their original height. A really important difference here though is that doubling 0 is still 0, so the vertex stays put. It's still going to be at the origin if this is all we are doing to the graph. So that makes the parabola go narrower because every point has to shoot higher. Okay, so let's reset this, and this time we'll put a half in front. So now every y value gets squished to half its original height, and the parabola goes out wider like that. So these multiplications can either make it narrower or wider depending on whether the number we're multiplying by is bigger than 1 or smaller than 1, okay? But finally, if we were to multiply by a negative there, then all the upward pointing y values have to now flip to point down, and we end up with a sad face. So that's what happens if the x squared is negative, it turns upside down into a sad face. And that's all we're going to do with these parabolas for starters. It's the simplest thing we're going to do with them, but in some ways it's the most important, because these actions can actually be done to pretty much any curve, not just parabolas, in exactly the same way, and it will produce the same results, so the movements and the stretching and all that stuff. So it's super important you understand these ways of changing the parabola, or whatever, because it'll apply to other graphs as well. So let's summarize the main features of these parabolas by bringing out this guy who's already been flipped and moved and stuff. One of the most important points to keep track of is this point up here. Now there's a few names, we can call it a turning point or a vertex, and right now it sits at the point -1, 4. And what's special about this point is that if we track through all possible y values the parabola could hit, it reaches its maximum value here. So we have a maximum y value of 4. Now, of course, if it was a smiley face parabola that had not been turned upside down, it would be a minimum value instead. But this gives a sort of extreme value, which is often practically handy, as we'll see shortly. And in these practical situations, it's often helpful to know which x value produces such an extreme point. And so in this case, the maximum value of 4 was reached at x equals -1. Other points of interest are, as usual, intercepts. So right here, the parabola hits the y-axis, and so we will still call that a y-intercept, and here it's at 3. Likewise, it hits the x-axis at these 2 points now. Okay, and because the parabola turns, there could be 2 of these places where we hit the x-axis. And so we have 2 x-intercepts at -3 and at 1. It's important here to also note the symmetry of a parabola. Notice how the maximum value, that vertex, is reached at x equals -1, which is exactly halfway between those x-intercepts. And that's true for every parabola. And so those are the main features of the parabola that you should be aware of, okay? But when might we encounter practical stories that involve these shapes? Since the equation we started with was y equals x square, that's likely to pop up in things like, say, area. Okay, so we might be building a garden and we have some control over the dimensions, how long and how wide, but we might be limited by the 100 meters of fencing we have. Okay, so areas often involve formulas that have these square terms in them, so x square or something. Okay, you might remember calling these guys quadratics from previous years. But the x square is what turns such a model into a parabola, rather than just a straight line or something. Or maybe even more direct, if we chuck a ball and track its path through the air, it roughly follows something like a parabolic shape, and we can approximately model it using a quadratic, a formula that has that x square guy in it. And so that's where we might be interested in those features from before. We might be seeing the maximum height the ball reaches, or trying to build the garden with the largest possible area using the 100 meters of fencing we had, or something like that. Okay, we'll run a proper example next time, but that's all for this one. Thanks for watching. See you then.